In this lesson, we will learn about observations about how atoms and molecules absorb and produce light, and how these observations contributed to the development of quantum mechanics. By now you should know that light can be separated into different colors, and one way to do it is to pass it through a prism as illustrated here. The explanation for this is that light consists of electromagnetic waves, and the wave behavior of light allows its different components to be bent at different angles. Here's a light source. Part of it is passed through a slit, then the light is bent as it goes through a prism. Waves with wavelength that we perceive as red get bent this way. Waves with wavelength that we perceive as yellow get bent more, and waves with wavelength that we perceive as violet get bent even more. We refer to the components of light from a given source as the emission spectrum of that source. When the concentration of atoms in a light source is low, as in a gas sample as illustrated here, we get what is called a line spectrum. What we see is a series of bright colored lines. When the concentration of atoms in a light source is high, as in a solid or a liquid, we typically get bands of color instead. Within a band, we say the spectrum is continuous. The emission spectrum from a given light source may or may not show all colors, but if it does, it would look like this. Note that for convenience, we are describing visible light in this lesson. Everything we are saying also applies to electromagnetic radiation outside the visible region. The absorption spectrum of a sample refers to the wavelengths of light that it absorbs. Here's a continuous light source. Its emission spectrum shows a continuous band of colors. If we pass the light through a sample before separating it into its components with the prism, we get something like this. The dark areas correspond to the wavelengths from the light source that were strongly absorbed by the sample. If the concentration of atoms in the sample is low, as in a gas as shown here, the dark areas can appear as sharp lines. Here's a dark line, here's another one, and here's a pair of dark lines. We would describe this absorption spectrum of the sample to be a line spectrum. To explain spectral lines, scientists had to make a radical assumption. The energy of atoms and molecules is assumed to be quantized. When we say energy is quantized, we mean that it cannot just have any value. Light is also assumed to behave as a photon when it interacts with an atom or a molecule. Similarly, light is assumed to be emitted by atoms and molecules as photons. A diagram like this is often drawn to describe or summarize what the allowed energy levels are for a given atom or molecule. This is called an energy level diagram. Each line in the diagram represents an allowed energy level. The Bohr frequency condition assumes that light can only be absorbed if the energy of the photon will take an atom or molecule to another allowed energy level. The energy of the photon of frequency nu is h times nu, where h is Planck's constant. For the photon to be absorbed, this must be equal to the gap between the initial and final energy levels of the atom or molecule. For example, we can say that if the energy of a photon is such that when absorbed, it will take the molecule from this energy level to this energy level, then the absorption would be allowed. In other words, we say that the purple arrows in this diagram represent examples of allowed transitions or allowed excitations. The term excitation means energy absorption. Similarly, any photon emitted by an atom or molecule must have an energy that corresponds to the difference between two allowed energy levels. Which of the excitations indicated by purple arrows in the diagram shown here requires a more energetic photon? The longer arrow represents a bigger energy change and will require a more energetic photon. Would the transition indicated by the red arrow be allowed? The transition would take the molecule from this energy level to this energy level, which is not allowed. The excitation is not allowed. The molecule will not absorb the photon. How would you describe the transition indicated by the green arrow? This involves a molecule losing energy. Since the transition takes the molecule from one allowed energy level to another, it would lead to the emission of a photon. The energy of the photon would be equal to the energy difference between the levels. Why do different substances have different spectra? The answer is simple. The allowed energy levels depend on the structure of the atoms or molecules. In other words, the spectra serve as an ID or fingerprint for the atoms or molecules that make up the substance. A water molecule and a carbon dioxide molecule will have different sets of allowed energy levels, but all water molecules will have the same allowed energy levels. Suppose a spectral line in the absorption spectrum of a molecule occurs at 500 nanometers. What is the energy gap between the two allowed energy levels involved? The energy gap is equal to the energy of the photon. We can calculate the energy of the photon if we know the wavelength. The energy of the photon is equal to hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. Plugging in the values, we get a photon energy of 3.973 times 10 to the negative 19 joules. This is the energy of the photon. An atom loses 2.50 electron volts as it emits a photon of light. What is the energy of the photon emitted? What is the wavelength? The energy of the photon is equal to the energy lost by the atom, 2.50 electron volts, or 4.01 times 10 to the negative 19 joules. Since the energy of the photon is equal to hc over lambda, where lambda is the wavelength, we can solve for the wavelength as hc divided by the energy of the photon. Planck's constant h is 6.626 times 10 to the negative 34 joules second. Speed of light c is 2.998 times 10 to the 8 meters per second. Plugging in these numbers and the energy of the photon, we can calculate the wavelength to be 4.96 times 10 to the negative 7 meters, or 496 nanometers. When a sample has a lot of very closely spaced spectral lines, the lines may appear continuous over a broad wavelength interval. We then see a spectral band. Spectral bands tend to be observed when atoms are closer together, such as in molecules, as well as in solids and liquids. In a solid or in a star, the photons bounce around so much that the observed emission spectrum resembles a blackbody spectrum. The momentum of a photon changes with every bounce, and so does its wavelength, since the wavelength of a photon is related to its momentum. Just a heads up, even if the transition satisfies the Bohr frequency condition, it may not be observed. Quantum mechanics actually puts additional restrictions on whether a photon can be absorbed or emitted by an atom or molecule. These additional restrictions are called selection rules, and we'll learn more about them as we go deeper into quantum mechanics. Let's consider a fictitious example to illustrate this idea. Suppose the four lowest allowed energy levels of a particle are A, 4A, 9A, and 16A. If this particle happens to have an energy of 9A, then it cannot emit a photon with energy other than 8A or 5A. Why? Well, if it emits a photon with energy 5A, its energy drops down to 4A, which is an allowed energy level. 9A minus 5A is 4A. If it emits a photon with energy 8A, its energy drops down to A, which is also an allowed energy level. 9A minus 8A is A. These are the only two possible emissions from 9A that will satisfy the Bohr frequency condition. However, there could be selection rules that would make one or both of these a forbidden transition. Bottom line, satisfying the Bohr frequency condition is necessary, but it may not be sufficient.